Hello everyone, this is Radu, I'm Rafał, and today we'll talk to you about GPUs, at least a bit, and which ones to use for local. As usual, we're consultants, and as usual, well, it depends which one. And it depends actually on multiple factors. Throughout the preparations of the talk, we actually got mind-blown with some things that we didn't expect. So, from the first principles, what it depends on? Well, it depends on whether you use it for training or whether you use it for inference. We'll focus on inference today, but those are two different use cases. In addition to that, it depends what you mean by local. And locality is actually not that simple as I may thought initially, because he thinks locality is different from what I think. From my perspective, local is here on this desk. For him, it's actually in the data center that you serve your own LLMs, not using the providers and so on. So you see, even we are not on the same page when it comes to local, but luckily we will get to the data for both use cases, right? So what it depends on actually. So first of all, let's go through a simple list. You can think, and this is like the first thing that comes into mind, that it depends on the model family and size. Throughout the test that we will show you, the ones that we did, we used a llama 3.2 3 billion version 1. However, in general, the more complicated, the bigger the model is, the more performance and memory you will need from your GPU. You can squeeze in a smaller model on your small laptop GPU, for example, but the ones that are big, 22 billion ones, for example, or larger, will require better hardware. It depends on the use case, apparently. So whether you use it for prompt processing or text or generation of tokens, it also depends. It dictates the performance of the actual use case. So for our case, for prompt processing, during the test, we did like 2,000 tokens for generation 300. It also depends whether you can live with a quantized model. So whether you're accepting the fact that you may have a less precise model, a less quality out of it. Of course, not at the cost, but as a benefit, you will be able to squeeze in that model onto your local GPU, for example. Of course, backend also dictates performance, and this was one of the things, and we will show that as well, that was kind of mind-blowing to some extent, that the performance may differ actually a lot, depending on the backend that you use for running the model. The driver, NVIDIA, so CUDA drivers, there are slight difference in performance. As usual, the latest and greatest will probably give you the best performance for your GPU, especially when running NVIDIA. The options, so how you configure the model, also matters. So in our case, we use, for example, batch size of 2048. We configure the flash attention and so on. Radu will talk about that a bit later. And the number of concurrent users, right? If I'm the only user, then I can easily run a smaller model on my local machine. However, if we will have 100, 200, thousands of users concurrently running, then the single GPU will not be enough. You will have to scale, and that's the thing. And finally, we'll show you nice things, which basically comes to a cost, right? You can, of course, take H100s and just run with it, but maybe that's not the best thing for your use case. You'll see, hopefully, you'll be able to at least judge after the talk. So we'll start with the model family and size, right? And the model size roughly predicts the performance. You can see here, to the left, we have two models, one that is 8 billion parameters and one that is 7 billion parameters. By the way, those are not our tests. We took you have the source of them at the bottom. But you can roughly see how those two models, like 8 and 7 billion, compares to the 32 billion DeepSeek model to the right. You can see that when you switch to 32 billion, you get 20% of the performance from comparing to the 7 or 8 billion. You see that the difference is noticeable here. So depending on which kind of model you want to use, performance will differ, right? And also different GPUs, and especially the better ones, show different gains depending on the model that you use. So again, you won't be just able to say that, okay, this model, like a llama, performs, gets like 300 tokens on RTX 5090, and I'll get the same performance out of different models. No, that's not the case. You will need to test, you will need to verify that on your use case, especially here, like look, RTX 4090 and RTX 6000, those are like the same graphics card when you compare the chip architecture, and they have roughly the same performance on the models that are here, right? But you can see that the gains from 5090, which is the newest NVIDIA architecture, is different, so to speak. Okay, and what's interesting, at least from my perspective, is that the latest and greatest GPU architectures are not that faster compared to the previous generations. Look here, for example, of course on the right we'll have the least performant, you'll see Apple Silicon there, which is kind of expected as NVIDIA GPUs here are specialized hardware for that use case. But for example, the H100 and A100, those are two different architectures, right? We have the H100, which is ADI, and the A100, which is Ampere. And you can see that the difference between them in generation of tokens for the quantized model Q4, you can see that those are not that different when it comes to performance. There is slight, like 10%, but remember, those are two different architectures, right? So we have a jump in the architecture and so on. We have the newest GPU, but newer GPU, H100, which is performing just slightly better compared on this particular model, in this quantized version and so on. We have to tell that. And also, as we mentioned already, like depending on where you're using your GPUs for prompt processing or generation, that also differs when it comes to performance, and we'll see that. For prompt processing, especially, the newest generation cards from NVIDIA shines. So you can see H100, 4090 here. We didn't have, by the way, we didn't have 5090 card to test. Those are tests done by, not this, but you'll see in just a second, tests done by us on similar graphic cards. And we get a similar performance comparison. You see far right, there is an Apple Silicon. Of course, this is not apples to apples comparison, by the way, because we are comparing laptops there, like M2 Ultra, M3 Max, to like very powerful GPUs on the left, right? So, for example, H100. But still, you see the difference in performance of those. So even like the M2 Ultra 76 core GPU is not comparable when it comes to performance to something like even 4090, which is a consumer grade, after all, GPU. And this is, for example, from our tests that we did. A few of those cards, both consumer and professional grade ones, were taken into consideration. And you can see that, for example, for performance generation, when it comes to tokens per second, the H100 was topping the chart with almost 300 tokens per second. On a llama model, the one that we selected, followed by GeForce 4090, then we had like a drop, and A100 and so on with the GeForce 3080. So you see the generations of GPUs are quite comparable to each other. When it comes to prompt processing, the consumer hardwares, which kind of was not expected by us, but the consumer hardware 4090 on Windows shines here, as you can see, even being better than H100, which is far more expensive when it comes to the MSRP of the card. Don't sleep.
All right. So let's talk about quantization. Quality-wise, I think the rule of thumb is if you can get a bigger model and quantize it to a reasonable level, it would get better quality than the equivalent smaller model, but like with F16. So what we did here is we exposed these models to a blog post that they've never seen, asked them questions, and then graded them as you do in school. And if we look at the lower level metric of perplexity, which is kind of a good predictor for quality, then you can see that the sweet spot is here at around Q4, Q5, where we can drop the size of the model quite a lot without losing that much quality. When it comes to throughput, if we take the exact same model, so not different models, but just the exact same model, F16 and Q4, you can see that the quantized model performs better when it comes to generation. However, and this was surprising at least to me, when it comes to prompt processing, it's the quantized model performs worse. This also depends on the backend. So not only different backends perform differently, but they perform differently on different GPUs. So let's take this example with 4090, two of them. You can see that llama.cpp beats VLLM. But if you look at two A10s, it's the other way around. So it depends on the configuration, I guess, as well. Driver also matters. We tried two different kind of close drivers. We got close performance, but again, it's not the same. And then options. So we used llama.cpp here, which is also what Vespa currently uses for model inference. And we tried pretty much all the combinations of build time options as well as runtime options. And we only found two that gave us better performance compared to the defaults. One, you probably expect this, batch size. If we can have larger batches, we're going to be more efficient. So we're going to have better throughput. And the trade-off is that there's more latency for each batch, which might impact the total latency. What happens with most backends, Llama being one of them, is they use dynamic batching, which is more efficient. And the point is you take micro batches and you create a larger batch out of them when you either reach a size limit or a latency limit. So you can be flexible here. And the second one is flash attention. So flash attention is a technique that can be used to have like fewer kernels or GPU functions run at prompt processing time. So you can see here that the generation throughput is exactly the same, but depending on whether the model is quantized or not, if we enable flash attention, we can squeeze quite a bit more performance of the GPU. And also flash attention has an impact on memory usage. So let's talk about that. I mean, I'll talk about concurrent users, but I think we have to start with memory. And in the case of llama.cpp, these are the three big consumers of GPU memory. There's the model itself, obviously. There's the context. And then there's the compute buffer that is used to process the current batch. So the model will consume more memory if it's larger, of course, and less memory if it's quantized, with the trade-off of performance. And the key value cache will depend on the context size and again on the model size. The key value cache can also be quantized, and again you'll get some trade-off in terms of quality. At least llama.cpp supports quantizing the key value cache. But you have to keep in mind that the context size of the cache is divided by multiple requests, right? So it's the sum of their contexts. And the buffer is for computing the current batch. So the larger the batch size, the more memory we're going to use there. And also bigger models will use more memory. And this is where flash attention helps. It reduces that compute buffer during prompt processing. So I'd like to touch on the question of whether we should have fewer bigger GPUs or more smaller ones. And I think the rule of thumb can be, let's use whatever gives us the best bang per buck. If it fits, right? Because if we have a larger model, it may not fit on a smaller GPU. Or if you have a larger context, it may not fit in a smaller GPU. With a larger context, however, we need to keep in mind that even if it fits on a larger GPU, we may not hit the throughput requirement, right? Because if you have a larger context to process, it's going to take longer to process it. So here's this test that these guys made where they took a bunch of GPUs and they kept increasing the concurrency, and then they said, okay, let's say our SLA is 10 tokens per second for each request. So some of the GPUs won't make the cut, even though they have enough memory to hold all the context. In our case, we had just one concurrent user, so to speak, so our total memory usage with the 2.5 GB model was about 4 gigabytes, so all the GPUs we tested had available memory. But if available memory, like if you want, let's say you do deep research and you need, you can allow more latency, but you'll want more context, then it may be that available VRAM is your bottleneck. And in that case, what you can do is you can take the GPU VRAM, you can subtract whatever the model consumes, and then that's what you divide by the $, and then you can get like bang per buck from the memory perspective. And this chart is what it would look like with a 4 gigabyte model, but it would look different with larger models, which will favor larger GPUs, or with smaller models, which will favor smaller GPUs. Which leads us to bang per buck. So when we did these calculations, we took the manufacturer recommended price. Your mileage may vary depending on where you buy or where you rent these from. So we took the, let's say, generation throughput, and we divided that by the price. And we notice here that the very cheap GPUs, both consumer and data center, tend to give the best bang per buck. Beyond that, it's the older generations that tend to be better. And that's, I think, goes back to what Rafał showed, that there's not that much difference when it comes to generation performance between these GPUs, but older GPUs tend to be cheaper, so that's why they give better bang per buck. If we look at prompt processing performance, it's different. It's still the very cheap ones that give the best bang per buck, but if you look at the rest, it's the newer ones that perform better, and that's because newer NVIDIA cards tend to be better at prompt processing. So kind of the reverse is here. So now it depends on your use case. Like if you do something like RAG, you're going to do prompt processing first, and then you're going to start generating, and you can stream that to the user. So probably what you really care about is prompt processing. But if you do something like deep research, then you're going to generate more tokens. So then, because you're thinking, as it were. So then the other part tends to matter more. That's what we had for now. You'll find us around if you want to talk some more. I'll be at the Vespa booth. The slides will be up, so all the links, all the graphs will be there. What we did with our tests is on GitHub. And last but not least, if you did not fill up the search survey yet, please do so. This is a survey that originated from the Solr community, but it's search engine agnostic, so it will help the communities of everyone, like Vespa, Elasticsearch, everyone. Yeah, results will be public, as you might expect, and all that stuff. And should I say anything else? No, I think I'm good. So if you do fill them up, drop by the Vespa booth. You might taste stuff that you've never tasted before.
Amazing, amazing. Cool. Questions? I was expecting more hands to be up, actually. And we have no online questions yet. I don't know, maybe people are taking time to digest what you guys have presented. Last call for questions? Oh, we have one.
Hi. The benchmarks on the consumer cards were done on Windows. Do you have any comparison between Linux and Windows performance?
We didn't do exactly like apple-to-apple comparison when it comes to graphics cards. We just took like 4090s and the consumer-grade GPUs, and we tested them on Windows. And the other tests, like the H100, apparently were done on the data center. So, so they were used in a Linux environment. However, we didn't do the test like 4090, in a Linux environment and in Windows environment and so on. I assume that would be a slight difference depending on the CUDA driver and how it is compiled on the Linux, but I wouldn't expect much of a difference, at least right now, especially since NVIDIA is all around in the data centers and so on. So right now it's pretty well supported. But we didn't do the tests, which is kind of a nice idea, by the way. Hopefully that answers the question.
More questions? Okay, then I guess that, okay, last one maybe.
Thank you. Just a quick question. So like we used to compare like 10 years ago or maybe more, the hardware and the cloud. So obviously the cloud is more expensive, but you pay by minute. So yeah, some of the architecture are better in the cloud. Like, did you try to like compare with cloud services like those on Hugging Face or OpenAI? I don't know.
No. The short answer is no, we did not. I think some of my colleagues did some of that. I don't want to give any names of providers, either cloud or whatever, but I think that's a very good point, that it may be that it's cheaper. At least what my colleague did, it was like, okay, it's much cheaper to use this hosted service to give you the LLM stuff directly. Because you're not only paying for GPU, you're paying for the whole machine, right? So that was his conclusion with that particular use case. But I think it's a good question.
Cool. I guess that calls for a big round of applause for Rafał and Radu. Amazing presentation. Thank you.